Alright, now let's reverse what we were doing in the previous video. In the previous video we were given the equation of the ellipse and we were asked certain information. Now we're going to get certain information and see if we can come up with the equation of the ellipse. We did this as far back as your Algebra 1 days when they would give you the equation of the line. They would ask you for stuff like the slope and the y-intercept, and then they would reverse it. They would give you the slope and the y-intercept, and that's for the equation of the line. So we know the basic form here, but we have to determine what our center is. We have to determine what a and b are equal to, and if a goes underneath the x, or if a squared goes underneath the x, or a squared goes underneath the y, based on how it's elongated. So first things first, I'm going to make a quick sketch of kind of what's going on here. This is just going to be really rough. So this is not part of the answer. This is just like scratch work here. And if I put at 3, 3 on the right, 3 up, there's a vertex, and at negative 3, 3, there's another vertex. 3 units this way, 3 units this way. Well, I know that my center is right smack dab on the y-axis, and it has a y value of 3, so my center is 0, 3. So I need that. I'm going to write that down over here, that my center is 0, 3. The distance from the center to the vertex is a, so I know that a is equal to 3. And I also know that my vertices are on a horizontal line, so this thing is elongated. I think I spelled that right, horizontally. So that means I'm going to have something that looks like this. I'm going to have x minus h, quantity squared over a squared, plus y minus k, quantity squared over b squared, is equal to 1. Now I have a, and I have h and k, but I don't know what b is. So I go back and I have the foci. The foci would be on the same axis, the major axis here. Notice it's 2 square roots of 2 and negative 2 square roots of 2 with the y values of 3. So it'd be like over here. This distance here to the one of the foci would be from the y-axis to this point would be a distance of this 2 square roots of 2. So that's c. c is equal to 2 square roots of 2. This one isn't so bad. Looking up, and I know that a squared plus equals b squared plus c squared. So that gives me 9 is equal to b squared plus, now 2 square roots of 2 squared would be 2 squared squared root of 2 squared, that'd be 8. So I have 9 equals b squared plus 8, which means b squared is equal to 1, which means b is 1. So now if all I need is the standard form of the equation, I believe I have everything. So this would be x minus 0, I'm going to take care of that in a second, quantity squared all over 3 squared, plus y minus 3, quantity squared all over 1 squared, is equal to 1. So I'm going to write this as x squared over 9 plus the quantity y minus 3, quantity squared, I'm not going to put it over 1, is equal to 1, and there is the equation. So we kind of work backward from the previous problems. Now we can also use ellipses in applications, and so I have an example of that. I hope I left myself enough space. I'm going to have to try to sketch a picture of what's going on here. A tunnel has vertical sides of 7 feet with a semi-elliptical top. Neat. The width of the tunnel is 10 feet and the height of the top is 10 feet. Alright, so we've got sides that are 7 feet. Here, let's see. 7 feet. The width of the tunnel is 10 feet. Right? Width of the tunnel is 10 feet. So this is 10 and this is 7. And then we have on the top something that maybe looks like that. Now I don't know if it's higher up and elongated vertically or if it's elongated horizontally like this might appear. It looks like a piece of bread. And what do we know? We know that the height at the top, now remember this is 7, but the height at the top here, this is 10. And we are to write the equation of the semi-ellipse. I'll show you what I mean by that. I don't think I've done that as an example yet, but I'll show you that in just a moment. Write the equation of the semi-ellipse. It says, for convenience, place the coordinate system at the center of the ellipse. So what they mean by that is to draw your set of axes like this. Oops, that was terrible. Let's see if we can do better than that. Got a little off. Something like this. Now, this distance is 7, this distance is 10. So that means that this distance, this is 0, 0, this distance here is 3. This is 10 across, so this is 5 this way, 5 this way. It is elongated horizontally. A is 5 and B is 3. So that would give me x squared over 25 plus y squared over 9 is equal to 1. Oh, it sure helps to have that diagram. Now they want the equation of the semi-ellipse. What they want you to do here is solve for y. So if I multiply through by 9, to get rid, trying to get the y squared by itself, I'm going to get 9x squared over 25 plus y squared equals 9. Then I'm going to subtract 9x squared over 25 from both sides. And then I'm going to take the square root, which would typically pick up the plus or the minus. Now, because of the way they suggested we set up our coordinate axes here, I want the part that's above. I want when y is positive. So I don't need the negative. That would be the part below that I haven't drawn in. So I'm just going to drop the plus or minus and leave it as a positive. Now, if you want, you could get a common denominator in here and try to simplify this a little bit. That would be 25, so that would give me the square root of 225 minus 9x squared all over 25. So that would give me the square root of 225 minus 9x squared all over 5. 5 now being on the outside, because you can take the square root of the denominator there. So that's the answer to part A. Part B says, to construct this tunnel, an engineer needs to know the locations of the foci. How far from the center are the foci? Well, the foci, here, I'm going to use a different color here, would be some like distance over here and some distance over here. So I need to know what this is. This is, remember, is C. Well, I have A and B. A squared is equal to B squared plus C squared. So that tells me that 25 is equal to 9 plus C squared. C squared equals 16, C is 4. So what I need to do now is I need to indicate that from the center, this is how far from the center of the foci. The foci are, this is in feet if I'm not mistaken, it is, are 4 feet from the center of the ellipse. Now, where are they located as far as the tunnel? Well, that would be what? 4 feet from the center of the road, from the center of the tunnel here, and 7 feet up. 4 feet to the left and 7 feet up, and we could write it out that way. But since it just talked about the center of the foci, or it just talked about the center, we're assuming that the center of the foci there. Alright, it's kind of different. Now, I haven't drawn and graphed a lot of ellipses, but you probably have seen some examples in the textbook and in the notes. And you notice that some ellipses are a little bit more elongated than others. Some are kind of circular looking, and some are kind of stretched out and kind of skinny looking. Well, there's a number that describes how elongated an ellipse is. And we call that number, we call that the eccentricity. Just like slope tells us how steep a line is when we graph it, eccentricity tells us kind of like how round or how elongated our ellipse is. And we define eccentricity, we call it E, makes sense, not E like the natural exponential base, 2.718, etc. But E is to represent the eccentricity here, and we define the eccentricity to be the value of C. Remember, that's the distance from the center to the focus all over A, which is the distance from the center to either one of the vertices. So it's C over A. Now remember, C is in between A and 0. C is smaller than A. So if C is smaller than A, then this number here, remember they're positive, this number here is always going to be less than 1. In fact, it's going to be between 0 and 1 because c can't be 0. So what does that tell us as far as if we know something about the eccentricity? Well, the closer e is to 0, the rounder looking the ellipse is. The closer e is to 1, the more elongated and stretched out looking and skinny looking it is. So that kind of gives us an idea based on the graph. Now, most of you probably know that the orbits of all the planets are elliptical. And even though Pluto has been declassified as not being a planet itself, we're just going to talk about them a little bit because we have some information. We're going to make a little story problem here. Now, remember what this means. It has an elliptical orbit, but it doesn't mean that the center is the Sun. The Sun is at one of the foci. So it's further away, then it's closer. You know, and that's how we end up with all the planets. Now, I think, if I'm not mistaken, the planet that has the, I don't know, the most round looking orbit is, I think it's Venus, but I'm not going to swear to that. All of a sudden, I'm kind of second guessing myself that I've got that wrong. I think I wrote that down somewhere. Yes, Venus, the eccentricity is 0.0067. So that's the most circular orbit. The eccentricity of Pluto, it's a little bit bigger, and I have it in the story problem. And what we're going to do is we're going to use the information that we know about ellipses to answer this story problem. So we're going to start off with Pluto is 7.376 times 10 to the 9th kilometers at its farthest point from the Sun. So I've tried to draw an elliptical pattern here with the Sun at one focus. There's the other focus, and then we're going to have this distance here being the point so that the Pluto would be at one of the vertices, the furthest away. There'd be a vertex here, there'd be a vertex here. At this vertex, it's furthest away. At this vertex, it's closest. I really need to know this distance because the question says, find the closest distance between Pluto and the Sun. So I've got to find x. That's why I went ahead and drew this out a little bit. I hope I can kind of squeeze all this in. Now, what do we have? Well, we have that this distance here is 7.376 times 10 to the 9th kilometers. That's A plus C. So I have A plus C is 7.376 times 10 to the 9th kilometers. And I also know the eccentricity, which is C over A. So C over A is equal to 0.2488. And I have a system of equations. So what I'm going to do here is I'm going to solve this system of equations. I'm going to take this guy, I'm going to multiply both sides by A, and I'm going to write C is equal to 0.2488A. And this guy here, I'm going to get rid of this scientific notation. It's times 10 to the 9th. So I'm going to need some words, I'm going to need some zeros here. So that's 7,376,000,000. I'm going to make a substitution. I'm going to plug this in for C, and that's going to give me A plus 0.2488A is equal to 7,376,000,000. I'm going to combine like terms here, so I have 1.2488A is equal to 7,376,000,000. And I'm going to divide both sides now by 1.2488. Whew. And I get A is equal to, I got to grab my calculator, and I don't have it. So hopefully I wrote it down on a piece of paper, and it looks like I did. I got A to be 5,906,470,211, apparently to the nearest kilometer. And so that's this distance here. which is this distance. Now I need to know what c is because I'm looking for x, and x is equal to x plus c is equal to a. So I need to find c, so I'm going to have to plug back in over here. Let's say right to here. So I have a, well actually a is this big number, 5,906,470,211 plus c is equal to 7,376,000,000. Subtract this from both sides and I get c is equal to 1,469,529 and 789, and that would be kilometers. Now that's still not my answer. My answer is x, which would be x here would equal a minus c, so I'm going to have to take this number and subtract this number to find x, and you'll just have to grab your calculator or your scratch paper. I'm going to go ahead and do it, and I get 4,940,422, and this is in kilometers. Can you see that? Oh, barely, but you can see it. So now, since it's a story problem, and I'm out of room here, I'm going to put my answer here. I'll just bring it right up here. And the question says, find the closest distance between Pluto and the Sun. The closest distance between Pluto and the Sun is, here it comes, 4,436,940,422 kilometers. Well, over 7 billion from the farthest point, a little less than 4.5 billion kilometers from its nearest point. But there's an example of using what we're talking about here with ellipses to actually solve an application kind of a problem. We did one here with the tunnel. We did one here using eccentricity. So give these problems some serious time and practice, practice, practice.